Okay, so let me wrap up what we discussed last time in the sense that I think we had kind of covered everything we wanted, but I just want to like emphasize this idea that so first there was the issue that we were looking at, which was multicollinearity. So the idea is that the columns of X could be linearly independent. Exact multicollinearity is where the linear independence assumption fails, actually. But it could hold. So the assumption of full rankness of X could hold, but we could still be close to being, or the columns could be close to being linearly dependent. And so we saw that this would cause an inflation of the covariance, the variance of the certain contrasts of the parameters. And one traditional approach is to drop some of the columns, some of the predictors. And the more modern approach, if you care about prediction only, is you can keep all the predictors, but you would add a regularization term, which is, let's say if you do least squares, it's a term like that, lambda beta squared. So you minimize the least squares loss plus a penalty on the L2 norm of beta. And it's easy to see if you take the derivative, say equal to 0, and argue that's actually the solution, that it just gives you a similar expression as the OLS, but with this extra lambda I added to X transpose X. And so the effect, if you do the eigen decomposition of this matrix, is to just add lambda to all the eigenvalues. It doesn't change the eigenvectors. And so when I invert it, I get 1 over lambda k plus lambda here. I believe I discussed this last time. So this extra lambda allows me to prevent this from going to, or blowing up if lambda k gets very close to 0. And so if you go back to through the arguments that we did, this would be the denominator of that expansion of the variance that we had. And so this allows me to control the variance. Okay, so I can trade off. What I'm going to trade off is the bias, actually. So I'm going to trade off a little bit of bias. So if this is non-zero, this estimator is going to be biased. But then I might be willing to allow some bias, but reduce the variance a lot. And this matters if you care about prediction, not necessarily you don't care about the beta hat itself, you care about predicting. I mean, if you care about the regression function and how close this is to the actual true regression function. So it may be that a bias is not an issue. So traditionally, what happens is that you let lambda depend on the sample size, and as the sample size grows, you're going to drop it. So asymptotically, the bias goes away as well as the variance. But for finite samples, this is very helpful. So we're going to come back to this idea later, hopefully analyze it a little bit more. But this gives us like a bias variance trade-off, which is very useful to understand theoretically. Okay, so this will come back, hopefully. And so that the wrap up for that lecture would be this formula we kind of derived, which nicely captures the decomposition of the variance of a contrast like A transpose beta hat in terms of the basically the directions of variation in X and the corresponding eigenvalues. And so small eigenvalues would correspond to directions that blow up in terms of the variance. And this is really highly related to the PCA idea, PCA of X, so the direction of maximal variance would correspond here to the direction of minimal variance because of the inversion. So this is the like roughly like 1 over, if you multiply by 1 over n, it's the covariance matrix of X. If you have a random design, we discussed, I believe in this lecture, we discussed this extensively. And then there's this inverse relation between the eigenvalues. And so if you understand PCA, which I encourage you to do, and I might assign a homework problem. If you haven't seen it, it's very useful to know. If you understand PCA, you basically understand this decomposition. It's very similar idea. And then there's this traditional approach, which is looks at a single coefficient, not necessarily a general linear combination, and then identifies is this factor. So you can write down the variance of beta hat j, and then we identify this factor that depends only on the interrelation of the x's. It was like 1 over 1 minus rj squared, if you remember. And this is called the variance inflation factor. This rj was the r squared of regressing xj onto the other predictors. And so this also has a very nice interpretation and connections to certain things like node-wise regression. And then there is this other measure that you can use, which is condition number. It's just the ratio of the lambda max to lambda min of X transpose X, which is a summary. This is going to be large if, again, you're close to losing like the full rank kind of property. And it's more general, and it just controls a lot of things about numerical stability of problems related to X transpose X. You may not even be able to calculate beta hat numerically accurately, because usually you have some sort of an iterative procedure, and the convergence of that procedure would be slowed down considerably. So, and then we kind of saw that this, like a fix, the two fixes basically just you drop some of the predictors that can be explained by the other ones. And this leads to the idea of model selection more generally, which we'll see hopefully maybe next week. And then there's another approach, which is you just keep everything, but you have a knob, you add a knob to like regularize. This is kind of the idea of regularization. And it's a very useful idea in statistics and allows you to, if you have a parameter, the tune to trade off. Okay, questions about this? It's the recap of last lecture. Okay, no questions. So today I'm gonna do kind of the like 90 degrees like rotation of the viewpoint. So it's like what we had in the previous lecture was what happens if we have issues with the columns. So the columns, one column is, or multiple columns are bad, or you shouldn't say bad, but there are problems between the columns. And now in this lecture, we're going to look at the case where some row might be a problem. Okay, so I'm going to use this notation xi transpose. So u to the xi is the ith column. But in this lecture, it's going to be the ith row. So xi transpose would be the ith row. So we're going to focus on rows of the design matrix. So we have like n rows. And then I have p plus 1 columns. And so we want to see, so even if the X is well conditioned, we still could have a problem. If it could be like the one of the rows or multiple rows like determine the fit or influence the fit of the model very significantly. So if I remove one data point or add it, or my estimator is going to be changed a lot. Okay. So a natural way to study this idea is via this kind of, it's a classical idea, at least in this paper, by Cook, like it would be how many years? Like 50 years next year, okay? So it's not a new idea. But this comes back. This idea is very powerful generally. And so if you want to study what happens or um, what is the influence of this particular observation, the idea is to remove it and see what happens. So you refit the model and then compare to the case where the observation was in the model. So remove row I and check whether the fit changes considerably. Okay, and this allows me to characterize which observations are, you could say outlier, but in general dominates the fit. Okay, and then maybe they're not outliers, but it would allow you to decide later whether you want to do something about it or not. So we're gonna introduce this notation, beta hat sub I. This is gonna denote the OLS fit from the data with the ith row removed. So notice that this is a vector. It's not the ith coordinate of beta hat. It's an entire fit, entire estimate of beta, but with I removed, the ith row. And I'm gonna, for simplicity of some of the arguments, I'm gonna assume that the ith row is the last row of the X matrix, but it doesn't matter. Without loss of generality, you can rearrange always. So, and you're gonna call the rest of the matrix Xi. So this is n minus 1 by p plus 1. And then corresponding y would be also yi, and then yi, okay? So what the idea is that we're gonna remove this row and this element. And now I'm gonna fit the regression to this new design and the observations, okay? So it's based on n minus 1 data points. And then I'm going to look at this quantity, which is xi transpose beta hat I, and you're going to write it like this, y hat I sub I. And then I'm going to pause here and ask you, what is the interpretation of this? Why I want to look at this? Anyone? Yes.
It's the product of the I throw on the X matrix with the beta hats.
That's true. But what is the interpretation? So that's like just a readout of what it is. So why would I care about this? Right. So it's an estimate of the observation. Okay, let me remind you. I mean, I'm changing the notation a little bit. So it used to be that we had like mu hat, which was like x beta hat. And then mu hat I would be your estimate of the mean. So you can write it in now in this format. Okay, if xi transpose is the ith row of x. So what I'm calling here in this lecture, these are, I'm going to call it y hat I. Okay. And so these are the same things as the fitted values, okay, or the prediction of yi. Or you can think of it, the prediction of mu I, really. But it's also a prediction of yi. But there's a difference between this and this guy, okay? And the difference is beta hat I. So what is the significance of, so this is also a prediction of yi. Yes?
Inputting the ith row of X using the OLS fit with that row removed.
Yes. So why this makes sense? So
that X row that
yes, yes. So the exact thing is this guy, the beta hat I has not seen xi or yi, okay? The critical part is that it hasn't seen the yi, okay? It doesn't know about the response. So in this case, beta hat has seen both xi and yi. So we included it in the least squares cost function. And so this already knows that like this yi correspond to this xi, but this beta hat I has not seen that data. So what I'm doing effectively is I'm simulating a future new data point. So I have the original data. I'm just artificially removing one row and one column and treat it as a new data that later I'm going to see. I'm going to see only this part, okay? And I'm not going to see yi. So I'm simulating what happens in the future where I fit a model and I receive a new xi and I'm going to try to predict. So this is like predicting a new data point using our model, okay? I'm simulating that. And the fact that this is in the kind of agnostic or does not know about y hat um, makes it a much more robust um, measure of what exactly our model is doing about that point I, as we'll see. If the yi's were included, there's like not in a straightforward, you cannot decouple, like beta hat is highly aware of that data point. So it would change the fit to align with that. But if I don't include it, you will see it would allow me to perfectly measure what would happen, what was the prediction, what is our prediction. So from a prediction perspective, this makes a lot of sense. So this allows me to, for example, if you look at the residual, um, this is the prediction error for a new data point. Effectively, I generated a new data point, xi, and I predicted it. So it has the two purposes. One is it gives me a way to measure the predictive power, and it also, as we'll see, it allows me to measure the influence. So we'll do both things at the same time. Okay, this is like a prediction error estimate, which is pretty good, as opposed to EI, which is not a good measure of prediction error. If you remember, you can always drive this down in our notation. So you can always drive the residuals, all of them down to 0 if you include enough predictors. But you can't reduce, like you can't drive this down to 0. This is like has that natural feature that it actually is an accurate estimate of the prediction error. And it also serves the other purpose of measuring the influence, as we'll see. Okay, so kind of everyone on board why I want to look at this. So this is the main quantity that we were going to study. But before doing that, we'll see, I mean, another measure which is called leverage. So influence would be basically how much this moves from beta hat. Okay, so I want to characterize how much beta hat I moves from beta hat. That's my basic job here today. But then this, as we'll see, involves basically two quantities. One is the leverage, which tells you how much yi hat depends on yi itself in the original like training data or fit. And this will factor into the second part. So let me start with this leverage idea. No, okay, before doing that, so this kind of a procedure that we're doing here is called leave one out or leave one out cross validation. It's like related to leave one out cross validation. And we are going to drive an identity for this, or rather, I prefer you drive it. I'm going to propose the identity. So there's an identity here that allows me to calculate this in closed form, and it's part of the classical diagnostic toolbox in regression, and these ideas resurface later. Like these were done like 50 years ago, but now in modern machine learning, very similar ideas are used to measure the influence of like individual training data point on your deep neural network or something like that. So I plan to maybe discuss this a little bit as well. So let's start with leverage. So leverage is easy to define. So you have, so this is before we do the kind of solve that problem that we had. So let's say we had mu hat, which is hy. So this is the projection of y onto the image of x. And now in this lecture, I'm going to call this y hat to be consistent. So y hat is my prediction of y. And h, you know, is this matrix. So if you look at the y hat I, you can see that it can be written in that form. It's just expansion of the matrix multiplication. And we notice that this is a linear function of the coordinates of y, okay? So whenever you have a function of yi, if I want to see how sensitive this prediction, let's say, is to the individual yi's, I can take a derivative. Okay, so in a sensitivity analysis, if you want to see, you have a function of multiple variables, you want to see how much changing this particular coordinate or component changes the value of the function, you can take the derivative, partial derivative, and that acts as a first order approximation. Okay, so the slope of change. So if you take the derivative, it's in fact a linear function, so the derivative with respect to the yj would be hij. And so if I evaluate that at I equal j, I just get hii. So this is actually capital Hii, but it's very common to write it in as little hii. Okay, so these are just the diagonal entries of h. So these quantities are called the leverage scores or leverage. So leverage of point I is this hii, and the interpretation is that how much, so if you remember what the derivative means, it's like saying if I, it's approximately like this, hii times delta. So if I change yij, if I make a delta yij change in yj, it's kind of transfers to y hat j via this relation. So it gets multiplied by hii. So if hii is large, a little change in y hat j would produce a large change in yj. If hii, let's say, is very close to 0 or 0, no matter what I do, like if I change yj, y hat j doesn't change. So it measures some sort of influence. It measures how much of an influence this point I will have on the fit up itself, not the entire regression line, but how much this individual data point can affect, the y of it can affect its own data point. Okay, it's like a local influence measure. And if you do the kind of just look at the row expansion that we had of x, you can just easily write it in this fashion. So xi transpose x inverse xi. It only depends on x. Notice that it doesn't depend on the y value of the ith observation. And there's a very nice way of writing it by centering, which I hopefully assign as a homework problem. So you can center the x's around their mean, and you get this expression. So this expression is like very easy to interpret. So this quantity here is, so basically it's saying it's 1 plus 1 over n. So this quantity is constant there. It's going to be always there. And then there's this 1 over n times this quadratic form. So this is, does this look familiar to people? We saw something like this in the discussion of GLS. So it was like a little comment. See how many have looked at the slides carefully. So there was this like little comment. If you go through the GLS, there's a little comment that you can define a general inner product between two vectors. If I have a, let's say if I have a positive definite matrix V, this sigma hat X is really the sample covariance. Covariance of Xi. So it's a positive, let's say semi-definite. In general, we're assuming that it's positive definite, which will be, this is really like, it's very close to X transpose X over N, but after you remove the mean of each column. So I'll assign it as a homework problem. But let's say assume that it's a positive definite, then it's invertible. And so if I have a V like that, I can define an inner product like this, A transpose V inverse A. Sorry, V. So this defines a well-defined inner product. And it would define a norm, which is, I can write it as this. So root A transpose V inverse A. And so if you compare these two, you see that this is really the norm of x minus xi minus x bar in this new inner product squared. Okay, so this is sometimes called the Mahalanobis distance. So if you imagine taking the, if you have a norm, you have a distance. So the corresponding distance would be A minus B transpose V inverse A minus B. So when V is the identity, this would reduce to the usual Euclidean distance, but now it's a different kind of distance. And appears a lot in the context, like in the statistics, okay? So you're measuring basically the difference of two vectors differently in different directions. The direction of the eigenvectors of V would kind of, and the eigenvalues would control how we penalize differences in different directions, okay? If you do the eigendecomposition of V, or this V here is going to be like sigma hat. Okay, so it's a measure of distance in a sense. It's like a different measure of distance. In particular, this is going to be 0 if xi is exactly equal x bar. So, and because you can see it's positive semi, the first it's a positive semi-definite matrix. And also, especially if I write it as a norm, you can see it's non-negative. So this part is going to be always greater than or equal to 0. So this is saying that the leverage is 1 over n at least, and potentially bigger. When is it big? When xi is far from the center of x data. And when is it small? When xi is close to the center of the data. Okay, so this measures basically like exactly kind of how outlier your data point is relative to the rest. Okay, so you compute the average data point, and if xi is far from the average, the leverage would be high. And if the xi is close to the average, the leverage would be low. Okay, so high leverage means being an outlier in the predictor space. Okay, that's kind of the summary of this interpretation. Does it make sense? Okay, and so we'll come back to this later, but doesn't say anything about why. So it could be, y could be like very typical, or it could be outlier, doesn't matter. It's just silent about the behavior of the y for that data point. So some properties of leverage are easy to get from the properties of the projection matrix. So we know that H is a projection of rank p plus 1. And in particular, you know that the sum of the elements, the diagonal elements of a matrix, is the trace. And we know that the trace of H is p plus 1. Anyone knows why the trace is p plus 1? Yes. Yes. So idempotent, but there's like a bridge. So it's idempotent, hence.
Since the rank is the number of ones in the diagonals is equal to the rank.
It's close. So the number of so the diagonals are not necessarily 1, but the eigenvalues are going to be 0 and 1. Okay, so the trace is actually equal to also, for a symmetric matrix, it's equal to the sum of the eigenvalues. And the eigenvalues of H are either 0 or 1, and exactly p plus 1 of them are 1, so you get this result. Okay, yes?
It's the case that eigenvalues are all between 0 and 1, right? They weren't always between 0.
They are actually exactly either 0 or 1. They're not, yes. So because of the projection matrix, that calls, like that's the consequence of the idempotent behavior. The HIs are between 0 and 1. The HIs are not exactly 0 or 1, okay? And so, so why they're between 0 and 1? They're bigger than 0 because it's a positive semi-definite matrix. And in fact, we saw above that they're actually bigger than or equal to 1 over n. You can improve this lower bound a little bit for this particular matrix. But why they're less than or equal to 1, there's this variational characterization of the eigenvalues. Have you heard about variational characterization? So if I look at X transpose HX, this is the quantity that appears if you take a vector and you apply, this is the thing that we look at when we try to basically define or argue about a matrix being positive semi-definite. If I look at the maximum value where I enforce this constraint, x, the norm of x is equal to 1, this maximum value for a symmetric matrix has a very nice value. So what is that? Anyone has a guess? Well, you think about it. So this is always going to be bigger than or equal to EJ transpose H or EI, let's say. EI transpose EI, and this is going to be basically HII. So EI is the ith basis vector, 0, 0. This is the ith element. So because EI has norm 2, and this side is the maximum over such vectors, this is a particular such vector, so this is going to be always less than or equal to that. And my claim is that this maximum is going to be 1. Anyone knows what this is in general equal to for a symmetric matrix? Yes?
Maybe like the norm 8. The thing was also like the large size about it.
Oh, yes, good. So this is, yeah, this happens to be the operator norm. What I want to look at is like the lambda max of H. So this is going to be the lambda max of H for any symmetric matrix. Is it going to be the norm as well? So it turns out to be like an operator. I mean, it is indeed equal to, that's a little bit more tricky. Okay, but it's equal to the lambda max. Okay, this actually defines a norm on the space of matrices, symmetric matrices, and it does match the operator norm, which is defined a little bit differently. But this is the part that we care about. Like, it's easy to show. So if this holds for any symmetric matrix. Okay, and you can show it using the eigenvalue decomposition. Prove using EVD. Just use the eigenvalue decomposition on H, and then do a change of variable. You can show this. Very nice. This is a variational characterization because I wrote the eigenvalue of the matrix as an optimization problem. Variational means like optimization. And so this is 1 in our case. We know that the maximum eigenvalue of H is 1, so this side HII is less than or equal to 1. Okay, this is a simple proof. And so we know a lot about these leverage scores, so they can't be too large. And I mean, the traditional approach is because they sum to p plus 1, there are n of them, their average is always p plus 1 over n. So you can always compute this, and then you compare, for example, with the average. If they're bigger than twice the average, traditionally, maybe people have flagged them as high leverage. So you have to worry a little bit about, we'll see when you have to be worried about. Is this okay so far? I think these are not very interesting, just like okay, but they can be done by linear algebra. The question is now, I want to measure how outlier I'm in Y, and that would factor also into the influence. So far, we measured how much we are outlier in X. And if you think about it a little bit, the first thing that comes to mind to check how much of an outlier point observation I is in YI is to look at the residual. Because residual tells you how far from the regression line you are. But on further thought, you could argue that this is not necessarily the best idea. Why it's not the best idea? Because if you look at the variance of EI, it looks like this. That's the variance. So that's the covariance matrix. Sorry. If you recall, the covariance matrix of EI is sigma squared times I minus h. If I look at the diagonal elements, it's just going to be sigma squared 1 minus HII. And if this has high leverage, let's say HII is close to 1, this would be close to 0. Okay, the variance of epsilon I would be close to 0. In the worst case, when HII is exactly 1, this would be 0, and the variance of EI being 0, and because it's 0 mean as well, it's going to be exactly equal to 0. So what this says is that like a high leverage point pulls the fit towards itself. So if you have high leverage, if the point happens to be an outlier in X, when you fit the regression, no matter how far off Y is from the other points, it will fit it would pull the regression line, the fitted line towards itself so that it reduce this guy. Okay, so it's going to be misleading. If I knew the actual error from the true regression line, that would be good, but I don't have that. I have the fitted one, and the fitted one is like attracted towards that point. Okay, so the raw residual is not necessarily a good idea, but there's a very simple fix. If I look at, for example, the variance of EI divided by sigma over root 1 minus HII, then this would be 1, because this is a rescaling by a deterministic constant. And then it's easy to, like, this comes out and then just cancels the variance. So this is going to have, this standardized version is going to have variance 1, so it's not affected by the leverage anymore. So this could potentially work as a very good measure, except that I don't know sigma, but when I don't know sigma, I can replace it with S, our estimate, and this, let's call this Ri. This is a fairly standard measure of how outlier you are in the Y direction. And there's maybe a slightly even better version where I replace the sigma with Si, like the parentheses, which is the standard error that I get in the regression where we removed one of the ith row. Okay, in the same setting that I calculated these things, I can also get an estimate of the variance. And so this one does not see the yi. And there's a little argument to show that, in fact, you can write this then in terms of like an independent quantity. So you can write it as the ratio to independent quantities, and this will have a t distribution, but with n minus p minus 2 degrees of freedom, because this is based on n minus 1 samples. This is slightly trickier, but either assign it as homework problem or you can think about it. But this will have an exact t distribution under the correct model if the ith row is coming from the same model. So then you can compare. You can look at the ith row. For example, when n is large, this is going to be close to the standard normal. And if, for example, this is like 10, it doesn't look good, because it like generally should be between like -2 and 2. And so you can easily measure whether your assumptions hold or not. I mean, it can be used both for diagnostics, whether the assumptions of the regression hold, so you can look at the residuals, and you can also detect whether it's an outlier or not, individual points, whether they're outliers. So does that make sense? I mean, this part, I'll let you think about it. It's not that obvious, because these two, I mean, here they're going to be problematic because they're really not independent. So S, if you remember, is just norm E squared divided by n minus p plus 1. So this is exactly one of the coordinates of the P here. So they're highly dependent. Although, I mean, for large sample sizes, this is going to converge to sigma by the law of large numbers. So it's approximately going to be EI divided by sigma root 1 minus HI. So it's not really that bad for n large. But if n is small, this is a little bit better. This still depends on, it may seem that it depends on, this still depends on all the data. And both depend on other data points other than the ith one. So they seem to be still dependent, but you can rewrite it using what we'll see later in a fashion that makes them independent. Or you can argue that easily. Okay, I'm going to move on from this. What I want to do is actually like discuss this problem that we started with. So you want to be able to see if you can calculate this beta hat minus beta hat I. And it turns out that I can do it in a single pass. I don't have to start removing one point at a time. I can calculate this for all I rather easily. And the basic idea is using this, you can call it the leave one out identity or the Sherman-Morrison someone else, which I forgot his name, lemma or matrix inversion lemma. It's a very useful lemma, which allows you to invert a rank 1 perturbation of a matrix in closed form. So this is a rank 1 matrix. U and V here are vectors. So you have a matrix A plus a matrix which is UV transpose. U is a column vector, V is another column vector. So this is like this times like a row vector. So it's rank 1. Have you seen this formula? How many people have seen this? Okay, if you haven't seen it, it's very useful. And can be used a lot. So this, I know, let's say I can invert A. I don't have to like do a complicated, generally matrix inversion is costly, okay? O of n3, let's say if you have an n by n matrix. Let's say I calculated the inverse of A, I just do an update, a little update. This update would be just rank 1, because this is like a vector again. This is a transpose of a vector, so it's easy to calculate. It's a rank 1 update again of a matrix. So numerically, it's very useful in many cases where you have new data points come in, you just want to update your estimates. And this is exactly the case here. So if I have, imagine I want to calculate the beta hat I, and the beta hat I is really xi transpose xi inverse xi transpose yi. And so I want to relate this to beta hat, which is beta hat has x transpose x inverse here. Okay. And the thing to notice is if I write, let's say this is x, the ith row is the last row, let's say, and this is xi, then x transpose would look like this, xi transpose here, and then the last row here would be xi, the last column. And then the dimensions here would match. So the dimension of this matches this, and the dimension of this piece is just 1 matches that. And then I can do, when I multiply, I can treat it like multiplying a row vector by a column vector. They're not vectors, but it behaves like that. So you get xi transpose times xi plus xi transpose. And so this is x transpose x. And if I rearrange, I get xi transpose xi is x transpose x minus xi transpose. Okay, now if you look at the inverse of that matrix, you notice that this is very similar to the structure above. So this is really A. You can call this part minus xiu, and you can call xiv, for example, or you can assign the sign to v, doesn't matter. And so you get x transpose x inverse minus x transpose x inverse, and then you get xi, this is going to actually plus, you get xi transpose, again x transpose x inverse, and then 1 plus xi transpose x inverse xi. This would be minus, actually. Okay? The minus is because one of the u's will be negative xi, or layer v. Okay? And so this part would be the leverage. This is HII, if you go back. And then we're almost there, so you have to just also multiply by. So I tried to do this in the morning lecture, and we like ended up like going nowhere. So I'm gonna assign it as a homework problem. So there's gonna be a little bit of a tricky application, but the key idea is this. Okay, so you do this is X trans, like I have to like also do X transpose. Let's say, okay, X transpose Y I have to relate to. This is X, you do X transpose Y as well. You get Xi transpose and then Xi, and then Yi is like Yi here. And this would give me Xi transpose Yi plus Xi Yi as well. And you can see again, this is like X transpose Y minus Xi Yi. Okay, and then you plug it into this formula. And we have this from here. So we have this from the first equation, and this one also relates it to that, and then you start to simplify. And once the dust settles, you would hopefully get this result. Okay, that's the hope. So this should be easy to do once you have a quiet place to sit for maybe half an hour and just do the calculations correctly so that you end up with the final result. But you plug these using the Sherman-Morrison formula. You can relate these two, and then you subtract, and then things would cancel out. And you end up, once the dust settles, with this very nice identity. So this is, you can see that it involves the original EI, and then the leverage scores that you saw there, like they appear because of this division by that quantity. And then you can also compute the residual in this regression, which is yi minus y hat ii. And that also turns out to have a very simple formula. Okay, so VEI divided by 1 minus HII. So we can compute both the perturbation of the fit, which is beta hat, and also the residuals using the original data. So, or the data from the original fit, using the original residuals. Okay, and so I don't need to. I don't need to refit the regression, compute these beta hats like I have to, if I had to do like just for every n, so for every 1 up to n, it would be costly. So I have to have like solved n regression separately. But this is saying you can compute this easily via this formula without actually fitting the regression, okay, multiple times. And you can already see the good thing is you can, if you look at this residual, again, this is the prediction error. So we're predicting, so this is the prediction of, you recall what this was. This is Xi transpose beta hat I. So this is the prediction of the response of observation I based on a model that has not seen that observation. And then you're comparing it to yi. So this is really a prediction error. Prediction error. A genuine prediction error, out of sample prediction error, if you want. And so you can see it naturally has this behavior that divides the EI by 1 minus HII. So if I use this as a measure of outlierness in Y, it's a good measure because it normalizes. It's similar in idea to normalizing by this, which we did it via the variance. This is normalized by 1 minus HI, which is like slightly different. But it has the effect that if a point has a large EI, right? Sorry, if it has a small, what do I want to say? Yeah, so the thing could have a large EI, but if it's going to be influential only if the leverage is high or low. Okay, So this should be go the other way. So let's say EI could be very small, okay? But the point could have high leverage. So HII is going to be close to 1. So then 1 minus HI would be close to 0 and it would blow up. Okay, so it would naturally say, it doesn't matter that EI necessarily is small. If the leverage is also large, then this is going to blow up. So this captures the idea that necessarily a small residual does not mean being a good point. It could be that the residual is small and naturally kind of balances the two out. Okay, so if EI is large, generally if EI is large is problematic, okay? Whether you have low leverage or high leverage. But if EI is small, it doesn't mean that it's necessarily a good data point. HI could be close to 1 and it could still blow up. So it's a natural measure of outlierness in Y, and we didn't get it by trying to measure influence, we did it by trying to predict. It's a very interesting idea. So you try to do the prediction, and the prediction error kind of has this natural built, like a influence measurement built into it. Okay, so this can be used both, as we'll see later. This in the model selection, we can use it as a prediction error to select the models based on it, and also can be used as a measure of influence. This also can be used as a measure of influence, as we'll see. So, but this is the key idea. Okay, so we do the leave one out cross validation. And in the context of regression, these are also called press residual prediction. Press is a statistic that you build out of this, and that's why it's called, we'll see it later. Okay, there's something about the Hoover loss that you can read. There's another way to deal with the outlierness. You could, so this could blow up, and you can replace the squared loss with Hoover loss, which is a robust loss, so that the influence is not bounded. So like the least squares could have unbounded, could lead to unbounded influence. So this could blow up, and so there's no control. You could have a data point that exerts infinitely high influence. But what if you choose the loss like in a slightly different way? So the so-called Hoover loss, this will have like a bounded influence per point. Just as side, in case you're interested, this is a classical area of statistics called robust statistics, started with Mr. Hoover and many other people, again, in around the same time as these ideas developed. But anyways, so this gets us to these 3 measures of influence that are in your book as well. There's this df beta, so difference in beta, which is really the quantity that we looked at. So it just measures how the entire vector, p plus 1 valued vector changes. There is the this measure, which is measuring how much y hat I is the prediction for observation I based on the whole data. This is prediction based on the data that we, so based on the data that where the ith observation is removed. And this is normalized by something that looks like it's a standard deviation. If you remember covariance of y hat I, which happens to be also, sorry, covariance of y hat, which we used to call mu hat. This is sigma squared h. So really the variance of y hat I is sigma squared HII. And so if I divide, let's say yi, this is the standardization, sigma divided by HII. And here we are measuring the distance, the difference between them in the on the scale of the standard deviation of y hat I. So this is kind of normalized. And this is, again, this is replacing sigma with that. So if you use the calculation that we did above about the EI, so you can rewrite it in this nice fashion. In terms of the TI was the studentized. So if TI would be what is it? EI divided by SI root 1 minus HII. I don't know if your book uses it or not. If you use S here, you can just replace it with RI as well. So depends which version you want to use. They're going to be close for large values of n. So if you do use S here, this would be Ri. But you can see this is an interesting way of saying it. So these studentized residuals measure outlierness in Y. The HI measures outlierness in X. And so this is an interesting measure of influence because it combines both. So whenever you have a measure of influence, usually it combines both. This is good, but this is the whole vector is hard to compare. Like, is it good? Is it bad? So Mr. Cook proposed to aggregate all of them. So rather than looking at this difference of vectors, we are going to measure basically the distance of beta hat and beta hat I in this kind of Mahalanobis distance. This is another case of a Mahalanobis distance. You can see this is like beta hat minus beta hat I norm squared in kind of this norm, okay? And the reason why this makes sense is if you look at beta hat minus beta, this we didn't do, but you can easily do. This quantity, we know that, so you know that beta hat is distributed like normal with mean beta actually, and variance sigma squared x transpose x inverse. So beta hat minus beta is normally distributed between 0 and variance or covariance sigma squared x transpose x inverse under the E2 assumption. So if you look at this quantity, this will have something related to the chi-square distribution after proper normalization. And if you divide by basically s squared times p plus 1, it's the same kind of story. This will have, because this is also chi-squared after proper normalization, they're going to be independent. This is going to have an F distribution, okay, with certain degrees of freedom, which I'll let you try to figure out. So given that what you know so far, you should be able to like prove something like that. Because this, like F is very normalized in a sense. So this is a proper normalization. Here we don't have beta, but what Mr. Cook proposes is this is beta, and just instead of beta, we use beta hat I. And so you're measuring them on the same scale that makes sense for measuring this guy. So this kind of accounts for the covariance of it. And this is accounting for this variance here. And then p plus 1 is like a degrees of freedom of that. So this is something on the scale of F. It doesn't have an F distribution, but you're not proposing to like do a proper test. It's just generally would be well behaved. Okay, and then the interesting thing is that using the formulas for this that we have in the previous slide, you can show that this is going to be Ri squared. That's this guy. Ri squared is just Ri is this standardized residual or something like this. And then again, you see this HII divided by 1 minus HII coming, okay? So this is, again, some measure of outlierness in Y direction, which is, in this case, Ri, and some, like, product of this, and some measure of outlierness in the X direction, which is HII, okay? I mean, this has the same format, like this is outlierness in Y, this is outlierness in X, and any good measure of influence in regression would have some sort of a behavior like this. So it combines both the leverage and a measure of what outlierness in yi. The good thing about this is it comes out of this leave one out idea. Okay, so naturally, this is very natural to look at, and this is a very natural way to summarize it, and it like automatically gives you this nice way. So rather than trying to come up with how do I measure like ad hoc way of like thresholding y, like HII and RI and things like this gives you a very nice measure of influence, okay? Does it make sense? Questions? So if this is high, generally this should be on the scale of F. Usually if it's bigger than 1, like much bigger than 1, then it's problematic, okay? That's the general idea. So generally influence is residual outlier, or like outlier in y value, times leverage outlier, which is outlier in x value. So any sort of reasonable measure of influence, we will have this. And it's calibrated again to the F distribution scale. So you don't have to worry about, like, for different problems, it will have different values. It's generally have to be like small, between like maybe 0 and 1, or maybe 0 and 2. So here's the picture, just to kind of argue. Let's see if you kind of get the ideas. So you have 3 points here. This is like simple linear regression. This point B here is, does it have high leverage or low leverage, or what is the situation with this? Is it an outlier in the x direction? No, it's like very close to the center of the data point. So this has low leverage. So generally, if you have low leverage, you're not going to exert too much influence. So it's like a sufficient condition, or like, sorry, necessary conditions that you have high leverage. If you have, so this is far away from, so the fitted regression line is the black one. This is far away from the regression line. So the residual is high, but the leverage is low. So it's not going to influence. You can see this orange one. The orange curve is what happens if I remove it and refit, and it's barely visible. So there's a slight difference, but it's almost like on the black line. So this doesn't have much leverage, although it's outlier in the y direction. So the residuals are high. It doesn't influence as much. This A is somewhere in between. So this has high leverage or low leverage. Kind of, yeah. So like medium to high leverage, and I would say high leverage. And then the residual, it's the situation is better than B, right? Its outlierness is not as bad as B, but it has, because it has more leverage, it's going to move the regression line more. So this is the red, like this is what happens if I remove A, the regression line moves to this red one. Okay, so you can see it's like the leverage allows me to like move the regression line with like much less outlierness in y direction. And this C is the worst case. It's like both high leverage, and also the interesting thing is that it's even, I think I'm not sure exactly, but it may be even less or of the same order of outlierness in as A. Okay, so the distance from the regression line is not that bad. It's even like closer than B, but this is the case where the leverage is causing like the regression line to be close to C. So this is pulling the regression line towards itself. Although it's outlier in Y, it doesn't look like it. So what happens if I remove C? You can see this just jumps to this guy. Okay, so C has a high influence. Okay, this I think is fine. Okay, so if I remove C, the regression line is going to move a lot, right? That is what happens with something that has high leverage and a little bit of outlierness. So what would have happened if C was here? Things would be much better. Okay, it will have high leverage, but it's not an outlier. So if C was on the regression line, then removing it wouldn't affect things. So to have an influence, you need both leverage and being far away in the y direction. Okay, does that make sense? This kind of summarizes a lot, right? And so C has high leverage and, okay, off trend. It's an outlier, let's say. And the other ones are kind of, so here the Cook's distance for A and B are like 0.4 and 0.1. And then for point C, if you calculate it, if it's correct, it's 2.7. Let's say if it's bigger than 1, yeah, we're going to say it's an outlier. The threshold is kind of arbitrary, but generally we discussed the F distribution. Again, this is not exactly F, but f being bigger than 2 is pretty unlikely. Okay, and then if you go to traditional diagnostic tools in let's say in R, there's this plot command. If you do the plot on an LM fit, so you do LM of something, and then you do a plot of it, it produces a lot of plots, diagnostic plots. So we can plot, for example, fitted values versus the residuals. This allows you to do some diagnostics. If there's a pattern in the residuals, things are problematic. So if you see the residuals are like this, maybe there's some nonlinearity in the actual model that you're not considering. But here, like the most of them are kind of random. That's good. But you see there are outliers here. So you can see certain. So at least this is outlier in the residual direction, but not in the x direction. This is in both directions. So kind of you see this plot makes sense even if you are not in the simple linear regression. So these bivariate plots you can plot. This you can't always plot because you'd have a regression surface which is high dimensional. This one is a QQ plot. You can do like theoretical normal quantiles versus the maybe standardized residuals or something like that. And then you would see you want to be close to the line and not like the tails are often kind of problematic. If they're like away from the line, they're like a alarm or warning. And then there's this other one which is y hat I against this. This is similar, but it's like in terms of the standardized or the studentized residual. This is a little bit more robust, as we discussed. This may not be robust necessarily. You can see the C kind of is bad here. This is the most interesting one, I would say. This is like we plot the leverage, HII, versus, let's say, RI or TI if you want. And this is if things are large here in this direction, it tells you that the point has high leverage. So it's an outlier in the x direction. If you go away in this direction or in this direction, it means that the point has like an outlierness in y direction. So if you're both, so if you end up here or here, then things are problematic. Okay, so the point has a high influence. And here you can also see these lines or the curves are kind of level sets of the Cook's distance. So on this line, everything has quick distance 0.5, and above this, basically here, everything has here and here, everything has quick distance 0.5, and above the other one, which is like this, here would be everything would have quick distance above 1, and you can see the C is like well in that region. Okay, B is okay because it's outlier here, but if you move it here, it would be like maybe problematic. So if it had more leverage, it would be problematic. But so far, it doesn't have much leverage on the regression line. Okay, so this kind of gives you a way to diagnose a bunch of problems with your regression. What you do with these, it's a different story, but they're either outlier or maybe they're important things actually. Sometimes you don't have to throw them out. Maybe they're telling you something. You have to pay attention that maybe this is usually like, if it's not an error or a measurement error, maybe your model is not correct. Maybe you should change your model or something like that. Okay. So we're almost done. I'm just going to maybe briefly mention this, maybe come back later and talk a little bit about this. So this is very classical, as I mentioned, like about 50 years ago. But this idea of influence has appeared in machine learning. It's like a statistical idea. But in general, you would have like a more general like parametric model. So you have like your model, you have a model like this that, let's say, take a data point and try to predict its y, and it has a parameter. It could be a neural network, like complicated nonlinear function. And oftentimes you observe a training data, so you have xj, let's say yj, and then you go and you have a loss function, and you try to minimize a loss function, which is something like maybe, I mean, this is the easiest thing to do is like, let's say this is the prediction of my prediction of yi, and then you compare it to yj, and then you square it, and then you average. over the training data. Okay, so this might be my loss, L of theta and X and Y. Okay, and then I can minimize this. This is like a least squares problem. It's a nonlinear problem usually because this is nonlinear, but I minimize this over theta, and then I get like an estimator. So minimize, you get theta hat, and then phi of theta hat. This function would predict my new data point. Okay, and if I want to see like how much of an influence each one of the training data exerts on this line, an idea would be to look at, again, exactly this quantity. So theta hat minus theta hat, I remove one of the data points, and I refit the model and check what is the difference. And in this case, the situation is not as easy as the regression because things are nonlinear, but you can do some approximation. So you could do a Taylor expansion, write down first order of optimality, and you get this nice kind of formula involving the Hessian. This is the Hessian of the loss. This is really all loss function. So this is this you can call L theta xj yj. Okay, so the Hessian of this would be the Hessian goes here. So this is really the Hessian of the loss, if you want, L theta hat xy, which is the second order derivative. It's a matrix. Should be evaluated at theta hat potentially. And then times the gradient of that, the gradient of the loss evaluated at that data point. Okay, and if you do this for example, the regression that we did, it would be very close. It wouldn't be exactly the same as the expression that we got for beta minus beta at I, but it's a good homework problem to try to. I actually forgot whether it's exactly equal to this or maybe different. But this you can use in machine learning, like you have an image classifier and then you want to see if the image of a cat had like a huge influence on the regression line or like the fit. And later you use in the opposite direction to attribute. When you predict, you want to see which training data points were actually involved in that prediction. That it can also use to do attribution of okay, and then there's kind of a yeah. So this is like a corresponding influence that's for attribution. So you can measure the influence of a data point on a test point. So for each data point, you can see like you can, instead of doing this, I can try to measure for a given test point what is this guy, right? Using a chain rule, I can measure the change in my prediction of a test point if I remove the data point I, and this is like the way to attribute, like give attribution. So if the point I has a high influence on this is what caused the prediction, for example, to be this particular label for this data point. Okay, so they rank data points based on their influence, and then they give you kind of an interpretation. Why the model is producing like a path for this image because of these images. So it's relying on this particular subset of the training data. It's a very interesting, like, ties back to the idea of like attribution or provenance, and I mean there are more ideas here, like in terms of interpretability and stuff. Okay, I'm going to stop here and then we'll come back, maybe talk a little bit about this. Thank you.